I'm here to discuss road drainage alternatives, which is the title of this presentation. Work this. First, as appropriately summarized in this quote, the three most important aspects of road design is drainage, drainage, and drainage. So why is road drainage so important? If road drainage is not adequately addressed, there can be adverse effects, including destabilizing sidecast material in hillsides downslope, gullying and channel network expansion, increased downstream sediment loads, altered stream flow and channel adjustments, and accelerated erosion and damage to the road. Let's take a look at examples of impacts that are caused by poor road drainage. Here we can see excessive rilling in a road surface with poor drainage. Note how the rills originate from around the bend in the road and travel for quite a long distance before draining off the road and forming a gully in the fill slope. Here we can see muddy water being intercepted in the road, concentrated, and flowing down wheel ruts. Think of the consequences of having muddy water like this getting delivered directly into a watercourse. This is a gullied road segment where stormwater flowed down the road and scoured out the running surface, creating a need to have the road repaired. Here's a relatively gentle road that water is allowed to pool, causing the road surface to soften and making the road nearly impassable. Oops. And lastly, this is a failed road prism caused by excessive flows that overwhelmed an oversized drain pipe and led to a debris flow that delivered to a watercourse downslope. You can see the drain pipe in the right side of the image, right here. To reduce road drainage-related impacts, we must design, construct, and maintain roads so they are as hydraulically invisible as possible. A hydraulically invisible road is one that maintains the natural flow of water within the watershed. I'd like to stress early in this presentation that the benefits in successfully treating road drainage are significant. It not only protects the natural resources, but it also ensures full use of the road and reduced maintenance costs. It truly is a win-win. So how do we go from a poorly drained road, similar to those that I've shown examples of, to one that is hydraulically invisible? To make this connection, I will discuss the types of road prism shapes, the various types of drain structures, and lastly, I'll briefly spend time discussing scour protection measures in ditches and at the outlets of pipes and dips. Let's get started by looking at the three common road prism shapes shown here from top to bottom that include crown roads, outslope roads, and inslope roads with an inside ditch. Here's a great example of a crown road. Crown roads are best used for high traffic volume conditions where 2 lanes of traffic are required. Crown in the center of the road divides the road runoff and shortens the distance where water needs to travel on the road surface. In this example, the road runoff flows into 2 roadside ditches. Where crown roads cross steep side slopes, only one inside ditch would be needed. Crown roads can be a benefit in flat terrain where drainage is difficult to obtain. Through the process of clearing and grubbing and the compaction of organic-rich topsoil, roads on flat terrain often develop bathtub cross-section similar to what's depicted in this diagram in the upper right-hand corner. This is undesirable because these bathtub road sections are difficult to drain. To address this, additional fill can be in-hauled and placed to build the road up, which is presented in the center portion of the upper diagram. Or trenches can be excavated on either side of the road and the excavated material used as fill to raise the road up. The downside of crown roads is that they require the largest amount of disturbance and are the most expensive to construct and maintain. This is an example of an outsloped road with a rolling dip. Outslope roads direct runoff from the cut bank across the road to the fill slope. Outslope roads have the smallest area of disturbance, are less prone to intercept groundwater, generate the least amount of fill that would be prone to erosion, and are often the cheapest to construct and maintain. Outslope roads should not be used on steep road grades in highly erodible soils or where slippery conditions are anticipated. Here's an example of an insloped road that has an outside berm and an inside ditch. This particular road is constructed on erodible, decomposed granitic soils. Inslope roads direct runoff inboard away from the fill slope and into an inboard ditch that is cross-drained typically by pipes. Inboard roads are well suited for steep road grades, slippery conditions, and unstable or erodible soils where you can direct water away from problematic areas. However, inboard roads are susceptible to storm damage due to the inlet of cross drains being plugged and the failure of tall cut banks. In addition, inboard roads can have a large footprint and are expensive to construct and maintain. Regardless of the road shape, drainage structures are necessary to properly control drainage. Here are a few of the more common types of drainage structures. We will discuss each one of these separately. First are ditch structures. The most common ditch structure is inboard ditches on insloped or crowned roads. In this photo, you can see this ditch conveys a lot of water and shows signs of scour and incision. Also note that there is no apparent cross drain within the frame of the photo, which looks to represent about 200 to 300 feet of road length. Here's another view of an inboard ditch that collects runoff from a road surface. Another type of ditch structure is an intercept or catchwater ditch positioned upslope of cut banks. Although not too common on low-volume roads, intercept ditches are used to collect and redirect runoff before it can flow over oversteepened cut banks that are prone to erosion. They are best suited in extremely wet climates where sheet flow is common. Due to their steep gradients, they are often required to have some sort of scour protection, which we'll address later. Next, we have pipe structures. Pipe structures on low-volume roads typically refer to cross-drain culverts that direct water out of inside ditch and discharge it below the road. The most common pipe used is galvanized corrugated metal pipe. However, in recent years, high-density polyethylene pipe is becoming more common. Cross-drain pipes should be sized based on the anticipated flows, the hydraulics of the pipe, and the anticipated debris loading. At a minimum, I would recommend never going smaller than a 12-inch diameter pipe, with 18 to 24-inch pipes being preferred. As you can see in the upper diagram, cross-drain pipes are typically oriented about 0 to 30 degrees perpendicular to the road, are inclined to match the native slopes, or are placed in the fill with a downpipe and or energy dissipator, shown here. Cross drains should never be placed to discharge onto a fill slope that is not adequately protected. In this photo, we have two examples of cross-drain pipe inlets. The inlet on the left is a typical inlet. You can see that this one is partially blocked by debris and difficult to see. The pipe on the right has a drop inlet structure. The drop inlet structure is expensive to purchase and install, but it provides benefits, including that it allows the cross-drain pipe to be buried deep in the road to protect it from damage. Can provide improve the hydraulic capacity of the structure. It allows for shorter cross-drain pipes to be installed because the pipes can be oriented perpendicular to the road. This is a potential cost savings. And it can provide some additional protection against debris, particularly if water is allowed to enter the top of the inlet through a grate such as this one. They also can provide grade control within the ditch, and they are less prone to damage by a grader when maintaining the ditch because they are more visible. Here are two cross-drain outlets. Note how they are installed. The one on the left was installed at a grade nearly flat. Thus, it is partially clogged with debris. It is good to install the cross-drain pipes with at least 2% more gradient than the grade of the ditch above the plugging. Above to avoid plugging. By this, I mean this is the grade of the ditch or road. The fall on the pipe, or the grade of the pipe, needs to be 2% greater. The pipe on the right daylights in the fill slope and has scoured a channel below. To improve this insulation, it appears that it would be best suited to receive a downpipe that would extend below the toe of the fill slope. Water bars are diagonal berms made by cutting and filling across the road. As you can see in the diagram, in cross-section, they typically have a high amplitude and a short wavelength. By amplitude, I mean the depth of the water bar, and by wavelength, I mean the overall length to install the water bar. Depths range from about 1 to 2 feet, and the overall lengths, depending on site conditions, range from about 10 to 20 feet long. Water bars are best used on low-volume roads meant for high-clearance vehicles and low traffic speeds. Typical problems with water bars is that they don't get properly anchored into the cut bank, allowing water to flow around them, and their berm can break down with just a few passes by a vehicle, rendering them useless. Note how the two examples on the right were well constructed. They are anchored into the cut bank and extend all the way across the travel surface of the road. They have held up to multiple passes of pickup truck traffic. Rolling dips are referred to as broad-based structures used in moderately traveled roads. Relative to water bars, the profile or cross-section of rolling dips have a relatively low amplitude and a long wavelength, as you can see in the diagram. Where necessary, the wetted perimeter of an outlet of the dip should be armored. Here's a photo of a large rolling dip. Although this is a good example of a well-pronounced rolling dip, it may not be able to accommodate low, long wheelbase vehicles such as lowboys or chip van. Keep in mind, if you are designing and building a road, you must consider the limitations to prevent this from occurring. It is best to outslope and maintain dips with a minimum slope of about 5%. Also, dips are not good on steep road grades, which I'll consider greater than 12%. This is mainly because they would require long, steep approaches. Overside drains are generally used on crowned and outsloped roads where an outside berm is used. Typically, they consist of an inlet structure with a slope drain. In this case, the slope drain is composed of an open-topped flume. However, closed pipes can also be used. Notice how the flume is properly anchored down the fill slope. Outlet protection is also provided to dissipate the high energy flows exiting the flume. Overside drains can be effective and more cost efficient than traditional riprap if installed and maintained properly, particularly where the fill slope has a long slope length. There is a risk that these drains can fail when runoff is diverted away from the inlet. They become plugged with debris, damaged by equipment through maintenance operations, or are overwhelmed by flows. In this photo, you can see how the inlet structure has a prefabbed cutoff wall to reduce the potential of piping and scour beneath the inlet. Here's a photo of an oversized drain that was washed out by storm flows. The photo was taken looking up at the road. You can see the cut slope of the road in the background and the remainder of a failed oversized. Outs are most common drainage structures along either insloped or crown roads on low sloping ground. They are commonly constructed with a dozer turning the ditch out into the surrounding slopes to allow runoff to disperse on the forest floor. Subdrains are drainage structures that address seeps or springs that impact the road running surface. Here you can see the asphalt has become alligator cracked and a pothole has developed as a result of the reduced bearing capacity of the saturated subgrade. There are two common types of subdrains. The first is an underdrain. Common underdrains are constructed to intercept shallow groundwater flow and direct it beneath the road surface through a pipe. An underdrain typically consists of filter fabric that is wrapped around coarse drain rock with a perforated pipe placed at the bottom. It is possible to eliminate the use of filter fabric if using a properly selected graded drain rock, since the graded drain rock will form a natural filter bridge. Choosing the correct gradation of drain rock, however, does require laboratory testing and experience. Problems I have seen with these drains is the top of the drain is constructed too close to the bottom of the ditch, right in this area, causing the drain to be damaged when the ditch is maintained. And drain rock is placed all the way to the surface instead of using a low permeable soil cap, which causes the drain to be adversely impacted by surface flows. I would recommend never mixing surface water with a subsurface drain. Surface water and groundwater should be handled separately. In this case, the ditch should handle surface water and the underdrain should handle groundwater. Second type of subdrain is a blanket drain. Blanket drain is a layer of wrapped drain rock that extends across the entire travel width of the road. The benefits of this type of drain is it provides a reinforced aggregate base to distribute traffic loads and provide drainage that can not only intercept shallow lateral migrating groundwater, but also intercept groundwater upwelling beneath the road. I typically would like to see at least 8 to 12 inches of drain rock with at least a foot of surface rock or soil placed on top to protect the integrity of the drain. However, the design should be based on the strength of the subgrade, hydrology, and the anticipated vehicle loads. Before I leave subdrains, I just want to take a moment to discuss geofabrics used in subdrains, where the primary function is to provide filtration. Both non-woven and woven fabrics can provide filtration, but unless laboratory tests are going to be performed on the native soils, I would suggest going with a non-woven fabric. The benefits of a non-woven fabric are that it has a high porosity and a high permeability, which equals longer flows or higher flows for longer, versus woven fabrics, which do have a high permeability, but because of their percent open area, they tend to clog. Gordon Keller will likely expand on the design and construction of properly functioning subdrains in his presentation on July 9th. Rubber diverters are constructed using a strip of rubber attached to wood that acts as a deadman. The idea is that the rubber is stiff enough to divert flows but flexible enough not to impede traffic. These structures have a limited lifespan and have a low hydraulic capacity. Open-top trenches or channels are constructed at an angle across the road. These structures are not that practical since they are expensive to install, can easily plug, require regular maintenance, and cause approach problems. They are probably best suited for private driveways. The last drainage structure I will discuss are grade reversals and rolls. A simple hump or dip in the road can form a grade reversal that can reduce the need for other drainage structures, including rolling dips, cross drains, etc. The rolls are where the road surface simply rolls from side to side. A great example of a roll is presented in this diagram where the road rolls from being insloped to outsloped and back as it crosses the stream. Another opportunity that rolls are effective are on roads with steep grades that could not otherwise accommodate a rolling dip. The place to stop and field questions.
Yeah, this is a little break that we take to people with different internet speeds to catch up. Some of you have already been commenting a little bit about the lag time between the presentation and the graphic. And we really can't, it's not avoidable. People have different internet speeds. Hopefully it's not too annoying to you. If there are any very simple questions that we could address now while we're catching up, put them in the chat box and we'll see whether we can address them. Okay, you know, Donna had one question maybe I could throw out there. I've seen these structures that you're talking about, like the rubber structures and the open box structures. You know, I've seen them in manuals and so on and so forth, but I haven't seen very many of them in California. Are they very common in California?
I have never run across them in California. Where I've seen them is in the literature that's primarily come from Oregon and Washington, but I myself have never encountered them.
Are they more suitable in climatic conditions like Oregon and Washington versus our more Mediterranean conditions, or I mean, are they suitable at all in areas where we have snow?
No, I think they're, you know, both of those structures have a fairly low hydraulic capacity. I think their main use is just to not to still provide some form of drainage, but not impede the flow of traffic. And to me, I think it's technology that someone has thought about and applied, and it's, you know, it's reached the literature, but I just don't know how practical that, you know, they are and how well they perform in the real world.
Great. Okay, so we can go on from here then, and we haven't seen any questions except mine. So let's go on back, Don. Thanks.
Okay. So far we have covered the 3 types of road shapes and the various types of drainage structures. So now we'll discuss drainage structure spacing. Drainage structures should be constructed at a spacing that would prevent excessive erosion, either in the inboard ditch, along the road surface, or downslope of the road. The spacing is a function of road grade, flows, soil type, ditch and road surfacing, and keep in mind the spacing must be modified based on landscape features, including topography, wet areas, landslides, etc. To recap somewhat what Drew shared in his presentation in Series 1, the erosive power of moving water is a function of the mass of the moving water and its velocity. The more moving water there is and the faster it flows, the more erosive power there is to create rills and scour gullies. So the main idea is that we want to space drainage structures close enough to shed the water off the road, thereby reducing the water volume before it has a chance to form rills and gullies. By doing so, the road will become naturally more hydraulically invisible. As I mentioned, the spacing is a function of road grade, hydrology, soil type, and surfacing. This diagram by Compstead et al. Is perfect for showing this relationship. On the left column, you have the percent road grade. The columns to the right are grouped by soil type, with non-erosive gravels and surfacing aggregate in group 1, highly erosive sands and silts in group 5 and 6, and clays in the middle in group 3. Notice that as the soils become more erosive and the roads become steeper, the spacing between drainage structures narrows. Also note in the footnotes, although I admit that it's difficult to read, the footnotes change the spacing based on slope position and aspect. Roads low in a watershed or with a northern aspect would have a tighter spacing. In addition to road drainage structures being placed at close enough spacing to avoid excessive rilling and gulling, they should also be placed based on the following, which we'll discuss individually. First, place structures upgrade of stream crossings to allow for filtering of sediment-rich runoff prior to entering the stream. In this figure, we have a road approaching a watercourse with a cross-drain pipe upgrade of the stream. The table below suggests the distance required for filtering based on the grade of the road and distance to the next cross-drain up road. So, let's see. With the next available cross-drain 600 feet up the road, the distance required for filtration is approximately 100 feet. Place drainage structures to discharge away from unstable or potentially unstable areas. Here we have a diagram in the upper left showing the geomorphic indicators associated with an active slide that include open tension cracks, abrupt and rough scarps, and toppled and jackstrawed trees. The diagram in the lower right shows geomorphic indicators associated with a dormant slide that could be prone to reactivation. The indicators are rounded, hummocky to benchy slopes, sag ponds, and swept trees. Here's another photo of an active and potentially active slide in real life. In the forefront is the lateral edge of an active slide, and off in the distance on the other side of the drainage, you see irregular hummocky to benchy slopes with areas of isolated debris slides extending down the channel below. You'd really need to do your homework in order to find suitable locations to discharge concentrated flow in this type of terrain. Place drainage structures upgrade of drainage divides to prevent water from one catchment basin mixing with and potentially impacting another catchment basin not conditioned to the additional flows. In this diagram, you can see catchment basins marked by the individual swales that the road crosses. The idea is to place a structure, shown here with the red arrows, before each of the basins to prevent the water from one basin from being diverted into another. By doing so, the road would be more hydraulically invisible. Place drainage structures to discharge onto divergent to planar slopes where possible to allow for better dispersion and infiltration. This diagram illustrates the differences between divergent slopes, which would allow flows to be dispersed on the top, versus concave slopes, which would concentrate flows, shown on the bottom. Headwall swales and colluvial hollows are examples of concave slopes that you would want to avoid. Place drainage structures both on the surface and, if site conditions warrant it, in the subsurface to drain wet areas present in the road prism. In this photo, a spring daylights at the foot of the cut slope on the right and travels all the way down the road to a crossing below. Attempts consisting of a cross-drain pipe and a water bar were made to place drainage structures upgrade of changes in road grade from low gradient to high gradient to prevent water from accelerating down steeper road grade and causing additional erosion. In this figure, you see the road climbs hard out of the channel bottom before transitioning to a more gentle grade just before reaching the ridge top. It is at this grade break, marked with a red arrow, that you would want to install a drainage structure. The last topic I will discuss is the use of energy dissipators. The use and selection of an appropriate energy dissipator should be based on in-field conditions and is a function of flow, soil erodibility, slope gradient, and slope roughness and cover. The areas where energy dissipators are required are where runoff flows are concentrated, such as in ditches, at the outlets of culverts and slope drains, and below rolling dips. Here's a ditch lined with riprap. Because of the placement of the riprap, the spacing between ditch relief structures can be increased. The size of rock and the thickness of rock should be based on the anticipated flows, the ditch geometry, including the cross-sectional area and the longitudinal profile, and the physical properties of the riprap, including density and angularity. Ditch dikes or check dams are another form of erosion control for ditches. Check dams reduce scour and channel erosion by reducing flow velocity and encourage settlement of sediment. A check dam is a small device constructed of rock, gravel-filled bags, logs, fiber rolls, pretty much anything, that is placed across the ditch. Typically, the center of the dam is the low spot, allowing water to be concentrated over the top of the dam and not allowing the water to flow around the edge of the dam. Check dams require extensive maintenance to remove the settled sediment. If this is not performed, the trapped sediment can be resuspended during subsequent storms or when the check dams are removed. Here's an example of a check dam constructed out of stake straw bales. Two references that can assist you in the design of appropriate energy dissipators for ditches include the publication by the FHWA titled Hydraulic Design of Energy Dissipators for Culverts and Channels, and a publication by Caltrans titled Stormwater Quality Handbook. Next, we'll take a look and talk about energy dissipators at the outlets of pipes and overside drains. In this photo, you see a watershed that was impacted by post-fire flows. Notice the in-channel check dams and the scoured slope below the outlet of the pipe. The most common form of energy dissipator at the outlet of pipes is the use of riprap. This diagram is from Caltrans and provides a simple design method to estimate the riprap size, depth, width, and length of the riprap apron below the outlet. The diagram uses the pipe diameter and the discharge as input parameters. Notice that the riprap is placed on top of a layer of geosynthetic fabric, and the thickness of the rock is about 1.5 times the maximum stone size. FHWA presents similar design methods based on the critical shear stress and the exit velocity of water as it leaves the pipe, which is similar to this that Caltrans developed. Another common method of controlling scour at the exit of pipes is by constructing a stilling basin that dissipates the energy naturally by creating a hydraulic jump downstream of the outlet as the flows reestablish equilibrium. The photo in the upper left shows a pipe with a constructed stilling basin downstream. The diagram in the lower left shows how a hydraulic jump is created as the water adjusts from one flow regime to another. And the photo on the right shows a real-world hydraulic jump that is being used by rafters. I acknowledge that on steep slopes, it would require a special set of circumstances for stilling basins to be an effective energy dissipator at the outlet of cross-drain pipes and overside drains. There are many other types of energy dissipators available, including this one that consists of geosynthetic fabric placed in a shingled overlapping pattern by Caltrans. Again, the two documents by FHWA and Caltrans are great resources to seek guidance in designing energy dissipators at outlets of pipes. Last, we'll talk about scour protection measures at the outlet of dips. Here you see a dip armored with one layer of uniformly graded, which is basically all similar size angular rock. Because of the highly erosive nature of the sandy soils making up the fill slope, storm flows were able to scour and downcut under and around the rock armor. This is a similar condition at this dip. Also note that the rock was placed only on the fill slope and does not extend across the travelway of the road surface. As a result, runoff was able to flow beneath the rock armor, causing a gully to form. In dealing with erosive soils such as this, it is a good practice to rock the entire bottom of the dip. The use of separation fabric beneath the rock in the travelway can be used to reduce the thickness of rock needed. As for the riprap down the fill slope, I do not generally recommend the use of fabric underlayment because it can be difficult for the rock to adhere to the fabric. Rather, I typically like to see the use of a more graded mixture of angular rock, which spans a range of sizes, placed in a keyway at the base of the fill slope. The rock should have a minimum thickness equal to at least 2 times the mean rock diameter, and it should extend the full length of the fill slope with a width wide enough to accommodate the flows. Although it is seldom done today for dips, the size of rock required can be calculated and is a function of the slope of the fill face, the density and angularity of the riprap, and the anticipated flows. For a typical installation, one with the fill slope inclined to 2 to 1, and with flows less than about 6 CFS, the common mean diameter rock would be about 10 inches. This is a document published by Robinson et al. That uses an empirical relationship to design rock chutes. To my knowledge, this is one of the best methods to apply when designing the size of riprap required as scour protection on steep fill slopes. However, professional judgment is required in applying this method on slopes over 40% or equivalent to 2.5 to 1. Here we have a great example of 2 closely spaced rolling dips with outfalls that have failed. In the photo, you can see that the loose outside layer of the fill slope had partially liquefied. It could be speculated that the failure was the result of poor construction practices in conjunction with limited scour protection. At a minimum, I would request that the fill slopes at the outfall of dips be overbuilt and then excavated back to expose more dense competent fill. In this photo, you can see how effective wood slash can be in capturing failed material. In this case, the wood slash was windrowed at the base of the fill. I think wood slash that is machined place, that is compacted into the surface of the fill, the full length of the fill slope below the dip is effective at preventing erosion by dispersing the flows and reducing flow velocities. However, fill should never be placed on top of wood slash. In conclusion, I'll stress again that road drainage is the most important aspect to consider in road design, construction, and maintenance. And if drainage is successfully treated, it protects the natural resources and ensures full use of the road with reduced maintenance and repair costs. With that, I can field questions.
Okay, so if people have questions, they should enter them in the chat box. I will note that there's been a little bit of an exchange here about the structures we were talking about, the rubber structures and such. Michael Wolpott is indicating that the structures might work well on a relatively steep road where a rolling dip wouldn't work, but only on a very low traffic road. And then Gordon Keller has said that he's seen them on roads, but they're problematic, only appropriate for very low volume roads and where you don't want to add a rolling dip, such as a steep grade. But generally he prefers rolling dips.
Yeah.
I know some years back there was a special issue of the Journal of Forestry on all these various road design techniques for forest roads, and you know, there were quite a few treatments on those kinds of devices, not just in Oregon, coming from Oregon, but also from the East Coast. So I guess they've been used more widely on the East Coast as well. So any questions from the audience there?
Yeah, and I would agree with both Mike and Gordon. With their comments there regarding those types of structures.
Use my editorial license here. I mean, there's been obviously a movement towards use of rolling dips and use of grade reversals and outsloping on low-volume roads in the last several years. But one of the things that is kind of interesting to me is that they can cause problems just as much as cross-drain, conventional cross-drains and insloped roads can, too, if you don't consider the outfall, as you've been discussing.
That's absolutely right. Even a well outslope road that pushes 5%, 6% can still become it still can divert water through ruts that will establish. So it's imperative that they have drainage structures placed at a fairly regular interval and well thought out in their location.
Well, not getting any questions here, Don. Maybe you've done such a good job that you've answered everybody's questions.